All right, so theorem 4.1.4 will tell us that for any subspace of any inner product space, V W perp is a subspace of V. So we can see it in the examples. We got nice homogeneous conditions here. We got a nice homogeneous plane here. And so they look like subspaces. Let's prove it. We need to prove the three properties. And so first, we need to prove that the zero of V is in W perp. So I'm going to take any W in W, the dot product of 0V in W. We actually saw in the properties that that was equal to 0. And so yes, 0V's in W perp. In fact, I mean, 0 is perpendicular to everything. All right, second thing, I'm going to take two elements. So V, let's call them U and V in W perp. Let's take any W in W. I need to show that the sum is perpendicular to W. Then since U is in W perp, we know that U, W are perpendicular. Since V is in W perp, I know that V and W are perpendicular. And so if I look at U plus V in W, that will be UW plus VW. You can see we're using axioms here. And so that's part of the reason we needed those axioms to be true, is we need them to prove things like the perpendicular is a, the orthogonal complement is a subspace. All right, so here I'm using some axioms. So axiom 2, and I get 0, and so that means U plus V is in the orthogonal complement as well. And lastly, if I take U in W perp and K in R, again, I need to prove that KU would be perpendicular to anything. Sorry, this is supposed to be a D. And so I'm going to take any element in W and show it's perpendicular to that. So since U is in W perp, UV is 0. And so KUW, now we're using axiom 3, and so we get K times 0, which is 0. So we proved the three properties, so yes, W perp is a subspace. Good. As soon as we talk about subspaces, we're going to start talking about bases, and we're going to start talking about coordinate vectors and all of this. So that's what we'll start doing now. So example 4.1.2, consider V equals R4 with the inner product. So close to the usual inner product, but with extra coefficients. That's close to what we've already seen. I'm going to take W to be the span of these two vectors. I want to find a basis for W perp. So I'm going to start the same way we started last time. I'm going to check a random element. So I'm going to take V to be A, B, C, D. V is perpendicular to U, and so that would be A times 1 plus 2, B times 0 plus 3C times 2 plus 4 D times 0. And so I'm getting A plus 6C should be 0. I want V to be perpendicular to W, and so again, that's A times 1 plus 2B times 0 plus 3C times minus 1 plus 4D times 1. I'm getting A minus 3C plus 4D. All right, so I'm really just applying this formula with these vectors. All right, so V is going to be in W perp if and only if A plus 6C is 0, A minus 3C plus 4D is 0. So that's 1, 0, 6, 0, 0. 1, 0, minus 3, 4, 0. I'm going to reduce. I already did. I got a thirds and minus 4 ninths. And so I have two free variables. Don't forget that column of 0 is still a free variable. And so what I get is that A is minus 8 thirds t, B is s, C is 4 ninths t, and D is t. And so my vectors are going to be 0, 1, 0, 0. That's not a 6, that's a 0. And minus 8 thirds, 0, 4 ninths, and 1. All right? So that's my basis. Of course, as usual, you could multiply this by a constant to get rid of the denominator, but since we're not doing anything more with it, I just decided to leave it and save a bit of room since we had none left. All right, so that's it for this section. Next section, we'll be looking at projections.